This video shows our work toward optimal tabletop rearrangement with multiple manipulation primitives. In the realm of robotics, one of the intricate challenges is the task of rearrangement using multiple manipulation primitives. See from the figures provided. A robot is presented with two images: the start, which shows a scattered array of objects, and the goal, illustrating how these objects should be neatly organized. The robot's task is to mirror the goal image by manipulating the objects from their initial disarray to the desired state. This challenge is a long horizon task and motion planning problem that demands strategic sequencing and careful movement. The robot must consider the order in which objects are rearranged, navigate them to their destination without interference, and ensure that each action paves the way for the next, without obstructing the final placement of remaining items. Consider how we as humans naturally interact with objects. We pick them up and place them where needed, yet not all items lend themselves to this straightforward approach. A box or book, for instance, might suffer damage or disassembly if not handled with care. And when confronted with heavier or bulkier objects, we might opt to use both hands or simply push the item aside to reposition it. Translating this task to robotics introduces unique challenges. To navigate these, we have equipped our robot with a suction-based gripper. This tool allows the robot not only to perform pick-and-place actions, but also to exert a top-down push on objects. This method sidesteps the limitations we encounter with fingered grippers, which may struggle to grasp objects that are too wide, ensuring that our robot can manipulate a broader range of items without the risk of damage. The introduce of push is necessary but also brings new computation challenges, as the push trajectories must be collision-free as well. We propose two methods for solving the problem. The first one is built on Monte Carlo tree search. The second one is a hierarchical best-first search. The design of the action space is pivotal to the performance of tree search algorithms in robotics. Given the uncountably infinite spectrum of possible manipulation actions, the strategy for action sampling becomes critical. Standard uniform sampling, while common, can lead to inefficiencies, especially when dealing with boundary conditions and specific edge cases. To address this, we implement 4 strategic criteria to refine our sampling process for determining the place final poses in pick-and-place and push actions. Random sampling. This introduces diversity into the action space, allowing for a broader exploration of potential moves. Proximity sampling. By sampling around the current and target positions, we enable the object to undergo minor, precise adjustments, facilitating finer control. Grid sampling. This method provides uniform coverage, ensuring that all areas, particularly the edges, are adequately explored. Goal-directed sampling. Actions are specifically sampled in the direction of the goal to streamline the path of the object towards the desired outcome. The Monte Carlo tree search, MCTS, is a heuristic search algorithm that is significantly enhanced by well-designed sampling strategies. However, the definition of the reward function is equally crucial to its success. A single reward at the goal state is often inadequate, especially when the planning time is constrained. To optimize the algorithm's effectiveness, we've developed a structured reward system. While it prioritizes reaching the goal state, it is meticulously balanced to prevent the introduction of excessive bias. In addition to the goal reward, we've incorporated a sub-goal reward. This acts as an interim reinforcement signal. When an object reaches its intended position, a fractional reward is granted, incentivizing incremental progress towards the goal. However, this approach presents a risk. The search could become ensnared in a local minimum. To mitigate this risk to some level, we introduce a base reward that normalizes the overall reward value to 0 at the start of the tree search process. This normalization occurs even if some objects are already in their goal positions, thereby counteracting any undue advantage from the sub-goal reward. Lastly, we factor in the cost of actions, which is calculated based on the time consumed by each. This cost ensures that the search favors not only success in reaching the goal state, but also efficiency in action execution. Our real robot experiments with integrated vision solutions demonstrate that our algorithms can be readily applied to interact with everyday household objects in real-world scenarios. In our problem definition, it is imperative to mention that the rearrangement occurs within a confined space, delineated by the red lines on the 2D workspace. Objects cannot be moved beyond these boundaries. This example demonstrates an arrangement where household items are methodically placed on one side, with electronic devices situated on the opposing side. For the experiment, we have constructed 40 varied scenarios, encompassing a mix of randomly generated cases and those specifically designed to present adversarial challenges. Our process adheres to the Percept Plan Act paradigm. Initially, the robot scans and interprets its surroundings. It then devises a strategy and proceeds to execute the corresponding action. This loop is repeated until the task at hand is successfully completed. Although the Monte Carlo tree search (MCTS) algorithm intrinsically incorporates stochastic elements, our algorithm is engineered to ensure that deviations are kept to a minimum. Distinct paths may converge to the same goal, and they do so with comparable temporal expenditures. In the course of our experimental evaluations, we have investigated a diverse array of objects and scenarios. Some involve large objects that necessitate a pushing action for relocation. In other instances, numerous objects nearly saturate the available workspace. Amidst this extensive and varied test set, we assessed our methodology against a fixed time budget, as the Monte Carlo tree search (MCTS) is an anytime algorithm. The time budget, indicated in the table next to PMMR, denotes the allocated time for determining each individual move. It has been observed that allowing a longer duration typically correlates with improved solution quality, though it does incur a proportional increase in planning time. These results were obtained on a multi-core CPU using Python. Looking ahead, we aim to harness the computational prowess of GPUs to further expedite the planning phase of our algorithm.